Right, so suppose you have some generic function of x. So we've got our x-axis, y-axis, some generic function of x. Let's call it f of x. And we want to find a definite integral. We want to find the integral of f of x from some value of a to some other value of b. And if you don't know what an integral is, it's essentially, I think you can think of it for now as just an area under the graph. So suppose we, and it's pretty common by the way, suppose we can't find an expression for the integral of f of x analytically. So we need to turn to numerical approximations if we want to find a definite integral. So the area in question is this area here, right? That's what we want to approximate. We won't be able to find it exactly, but we can approximate it. So to start, let's divide the x-axis into a bunch of, let's just split up the x-axis, right? Yeah, okay. And so these lengths here, they're all equal. So this is just small delta of x. I'll just call it small delta of x. And the lowercase delta just indicates a small change in, a small change in x. So these are all the same length, and they're all small changes in x. So now what we're going to do is split this area into a bunch of rectangles. To do that, we're going to pull this up to the function, like that. Now, what I'm doing here is, do that again. I am dividing into rectangles where the midpoint of the width of the rectangle intersects with the function of f of x. So this point here, and this point here, and this point here, and this point here, and this point here. It's not so clear with that one, but they're the midpoints of these rectangles. And the reason I'm doing that, as opposed to doing it on the left or right corner, where the left or right corner intersects with the graph, is so that this area here roughly cancels out with this area here, and similarly this area here roughly cancels out with this area here, and this area here roughly cancels out with there's a small area in there, right? And this area here will roughly cancel out with the small area in there. Now, it's not reasonable, it's not completely reasonable to assume that they will cancel out, but it'll give us a better approximation by doing it this way. Okay, now let's call the y coordinate of these blue points of intersection. Let's call this y1, let's call this y2, let's call this y3, let's call this one y of n minus 1. So there's a skip a few in the middle there. And let's call this one y of n. And then the area of this rectangle, let's call that a1, and the area of this rectangle can be a2 and a3, and again we're going to skip a few, and an minus 1 and a of n. So I've only drawn 5 rectangles, but in reality there are n rectangles, and we choose n, by the way. N is a value that we choose, and the greater the value of n is, the more accurate the approximation will be. So the integral, we can see, actually before I do that, let's come up with an expression for delta x. What is delta x? Well, delta x, well, we can see that this width here is n lots of delta x. Why do I say that? Because there's n lots of delta x, because there's n rectangles and each of them has a width delta x, so there's n widths delta x. So that whole length, n delta x. So if we take a and add that width, n delta x, it's going to give us b, right? A plus this width gives you b. So just rearranging that, delta x equals b minus a over n. That's pretty important. Okay, back to our integral. We can say that the integral, that's to say the area under the graph, from a to b of the function of f of x with respect to x can be approximated by the rectangle rule, or the midpoint rule I should say, where we add all these areas up. So it's approximated by a1 plus a2 plus a3 plus da 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 plus all the areas in the middle plus a of n minus 1 plus a of n. So there's n rectangles and we're adding them all together. Now that, if we consider, well, what's the area of a rectangle? It's just its base times its height. So it's its base, which is delta x, times its height. And what's its height? Well, its height's just y1, right? Because the height of this first rectangle here, that's just y1, and the height of this last rectangle is just y of n, right? So the height of the first rectangle is just y1, so it's just d of x times y1, and the area of the second rectangle is its base, which is also delta x, times y2 this time, right? And similarly for the third rectangle, all the way up, including all the rectangles in the middle, to the n minus 1th rectangle, n minus 1 plus delta x times y of n. Okay, and we can factorize out the delta x, can't we? So that's going to be y1 plus y2 plus y3 plus all the y's in the middle plus y of n minus 1 plus y of n, where delta x is, as we've said, b minus a over n, right? And that is the midpoint rule, but it's a little bit more complicated because y1, well, what is y1? Well, let's find the expression for that. Actually, before I do that, I'm going to use some sigma notation. I like sigma notation. If you want to use sigma notation, that's great, and I encourage you to do that. I don't like that sigma. That's better. From some value of I is 1 to n of y, right? And if you haven't done sigma notation, don't worry, but just take that as true. And that is the rectangle rule. These two, where delta x is that. But what's yi, I hear you say? Well, yi is just f of xi. Okay, so here we have y1, so x1 is just going to be there, right? So let's call these x1, that's going to be x2, that's going to be x3, that's going to be x of n minus 1, and that's going to be x of n. I realise you can't really see that, but just, there you go. Okay, so the coordinate of this blue point is xn, yn, right? So if I ask you what y of I is, well, you can tell me that y of I is just f of xi. yi is just f of xi. Okay, now you have to tell me what xi is so we can find what that is. Well, xi, okay, let's start with x1, for example. x1 is going to be half the length of dx. It's going to be a, the value of a, plus half the length of dx, value of a, plus half the length of dx, right? Okay, so that's going to be a plus dx over 2. Okay, now what's x2? Well, x2 is just going to be a plus dx plus another half dx, right? Or you can think of it as x1 plus delta x, right? I realise I'm using d and delta interchangeably, but just go with it. So x2 is going to be a plus delta x over 2 plus delta x, which is a plus 3 delta x over 2, and it's also x1 plus delta x, right? Now what's x3? Well, x3 is just a plus delta x plus another delta x plus half a delta x, right? Because x1, x2, x3, they're halfway. They're halfway across this width here, right? And because their corresponding y coordinate is halfway across the width. So, because that's what we've said it is, right? So x3 is just going to be x2 plus delta x, which you'll find is a plus 5 delta x over 2, right? So this is x1, this is x2, this is x3, right? We want to find an expression for xi. So we can see that x1 is a plus 1 lot of delta x over 2. x2 is a plus 3 lots of delta x over 2. And x3 is a plus 5 lots of delta x over 2. So you can think of it kind of like a series, right? So we've got, let's call it M, so we don't have confusion. We've got a table, right? We've got M, and then, so when M is, we'll do it like, when M is 1, we've got 1 lot of delta x over 2, right? So it's 1 lot of delta x over 2. Number of delta x over 2 is 1 lot. When M is 2, so that's, actually I can put this as I, can't I? When I is 2, you've got 3 lots of delta x over 2, right? When I is 3, you've got 5 lots of delta x over 2, like this. So we can see these are like the odd numbers, right? So we'd expect that to be 7. We'd expect it when I is 5, that's to say x5, we'd expect it to be a plus 9 delta x over 2, right? We'd expect that to be 9. So, well, what's the equation for this? What's the nth term, the ith term, I should say, in the sequence? Well, it's just 2i minus 1, right? So the number of delta x's over 2 is going to be 2i minus 1. So, xi, we can say, is going to be a plus 2i minus 1 lots of delta x all over 2. Okay, so I hope that makes sense. I realise that might have been slightly confusing, but you know, have a think. You'll see x1 is a plus 1 lot of delta x over 2, x2 is a plus 3 lots of delta x over 2, x3 is a plus 5 lots of delta x over 2, and these are the odd numbers, 1, 3, 5, right? And they're the odd numbers which take the expression, in this case, 2i minus 1. So xi is going to be a plus 2i minus 1 lots of delta x over 2. And remember, delta x is just b minus a over n. So we can say that that's the same as this, b minus a over 2. Okay, so that gives us xi, and from xi you can generate yi, and from yi you can generate your approximation for the integral. So let me write it finally. It's like a final statement almost. The integral from some value of a to some value of b of some function f of x with respect to x can be approximated by the sum of all these rectangles underneath it, right? And that we've shown is delta x times the sum from I equals 1 to n of yi, which is, and you can also say, instead of saying that, you could say the sum from I equals 1 of f of xi, like this, or you can do it as I've written it there. But this is important because this is how you generate your xi terms using that expression there. So to find an approximation for the integral, you generate your xi term, then from that you use the equation of the graph. You need the equation of the function f of x to generate your yi terms by this expression here, because yi is just f of xi. Then you add all of those yi terms together, multiply them by delta x, where delta x is b minus a over n, and that gives you an approximation for the integral. So I realise this can be difficult to compute manually by hand, but you can get a computer to do it, and you can write a relatively straightforward Python script to do it for you. So if you'd like to see that Python script, if you'd like to see me explain that and show you that, then let me know down in the comments. I can explain that, or I can just link it to you and you can have a play around. You can see how when you change the value of n, that's to say when you increase the number of rectangles you're dividing the area into, you increase the accuracy of your approximation. So if you'd like to see that, let me know down in the comments. Also, if you'd like to see other methods of numerical approximation, do let me know. This is just one. This I don't think is the best one, but it is, relatively straightforward compared to some of the other ones. But there's also the trapezium rule, which isn't that much more complicated at all, and it gives you, you could argue, a better approximation. And there's some cool stuff with concavity there. So let me know down in the comments if you'd like to see that. But thanks for watching. I hope it all makes sense, and I guess I'll see you next time.